We now have bagged some of the biggest black holes ever recorded in the history of science that have gobbled up over 20 billion stars. What if we told you that Michio Kaku finally has the answer to what's inside a black hole? This animation represents what scientists think is the brightest object ever found in the universe, and Australian astronomers discovered it. The question has persisted for centuries. Some believe that the hole leads to a whole other universe, while others believe that it leads nowhere. But the answer is something you could have never expected. The hole is more than just a dark, scary thing in space. It's much more complex than that. Join us as we get into what Michio Kaku has to say about the inside of a black hole. The great discovery not so long ago. Astronomers experienced a big moment. They were celebrating a groundbreaking discovery because, after a $2 billion expenditure, the Hubble Space Telescope had finally gotten its hands on the ultimate prize, a black hole. The EHT zoomed in on the event horizon, that point of no return in space where even light can't pass through. The picture showed where photons vanish into the black hole's abyss, and it wasn't just big news, it began a whole new research into the black hole, giving astronomers an actual visual of these mysterious space entities. By the time it was 2021, astronomers came out with a fresh take on the colossal M87 black hole. They used polarized light this time, catching a new glimpse of the black hole. But what was that going to do? Polarized light has light waves which help brighten out even more details, shining a spotlight on the magnetic ring around the black hole. Then in 2022, scientists unveiled the first ever picture of our own galaxy's supermassive black hole, Sagittarius A star. This is a supermassive black hole that is 4 million times heavier than our Sun and sits about 26,000 light-years away from us. But what does it really look like? Black holes aren't just dark voids, they've got layers. First, there's the event horizon, the no-go zone around the black hole's mouth where nothing comes back, not even light. Then there's the singularity, a point in spacetime where all the black hole's contents get crammed. It's like the center of cosmic gravity pulling everything toward itself. But here's the thing, you can't just zoom in with a telescope and take a pic. Astronomers have to get creative, and they pick up radiation signals when things get consumed by these cosmic vacuums. Supermassive black holes existing in galaxy cores often hide behind dust and gas, making it tough to see what's there. But have you ever wondered what's inside a black hole? Well, it's a ride into the unknown. And where do black holes lead? That's the big question. It could lead you to other dimensions or even parallel universes. Sometimes, as things spiral toward a black hole, they don't vanish, they bounce off and shoot out in cosmic jets at crazy speeds. Even if the black hole stays hidden, these jets light up the universe like fireworks. The controversy, the 2019 discovery also reignited an age-old debate. What happens if you fall into a black hole? Do you get squished by its immense gravity like most scientists think, or do you shoot out into a parallel universe or a different time altogether? Michio Kaku has answered all of these questions. A black hole is almost like a massive dead star whose gravity is so intense that even light can't escape. That's where it actually gets its name from. Since a black hole is invisible, NASA scientists have had to look at the M87 galaxy, which is 50 million light-years away. That's where they spotted one. What they found was mind-blowing, a swirling storm of superhot hydrogen gas spinning at 1.2 million miles per hour. To corral this chaos, there had to be an object at the center with a mass of 2 to 3 billion suns, enough to trap light. And that's what a black hole is. There has been quite a lot of controversy around black holes. In 1963, a math whiz from New Zealand named Roy Kerr used Einstein's gravity equations to describe spinning black holes. But here's the twist, Kerr's model suggests that if you fell into a black hole, you might find yourself hurtling down a tunnel, which is also known as an Einstein-Rosen bridge. You would later pop out of a white hole in a parallel universe. Kerr's theory flips the script on black holes collapsing into a point. Instead, they morph into a ring of fire. Because this ring spins so fast, it doesn't collapse. If you shot a probe through it, instead of getting squashed, you might land in a different universe on the other side of the wormhole. It's like a cosmic shortcut connecting parallel worlds or distant corners of our universe. Kerr's wormhole. Imagine a Kerr wormhole similar to Alice's journey through the looking glass. When Alice stepped through the mirror, she entered Wonderland, a world where animals spoke in riddles and common sense took a backseat. Similarly, walking through the rim of a Kerr ring could transport you across the universe or even back in time. It's like having two interconnected universes, each offering a portal to somewhere entirely different. Some physicists have entertained the idea of using black holes or wormholes as shortcuts or even time machines. In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the center of the black hole. However, there are skeptics in this cosmic debate. They acknowledge that numerous wormhole solutions have emerged from Einstein's equations, showing they aren't mere fantasies. Yet, critics warn of potential instability or deadly radiation and subatomic forces at the wormhole entrance. This debate has sparked very passionate discussions among physicists. The challenge lies in the fact that Einstein's equations falter at the heart of black holes or wormholes, where intense radiation and subatomic forces could collapse the entry point. Einstein's theory primarily addresses gravity, not the quantum forces governing radiation and subatomic particles. What's required is a unified theory, a theory of everything that seamlessly combines quantum theory with gravity to tackle the mysteries of quantum black holes. Superstring theory, the theory of everything. The quest for a theory of everything in physics is like the ultimate puzzle, trying to blend two major scientific heavyweights, Einstein's theory of gravity and quantum theory. Einstein's gravity theory is all about the big things, galaxies, black holes, and the mind-blowing beginnings of the universe with the Big Bang. On the flip side, quantum theory zooms into the tiniest particles and the world of radiation. The crazy thing is, even the big names in physics like Einstein and Heisenberg scratched their heads over how to merge these two into a single super theory. Here comes the superstring theory. This theory is all about connecting gravity with radiation, which is key to cracking puzzles like quantum wormholes. Superstring theory flips things around for particles. It says they are not just tiny points, but vibrations of super tiny strings. Imagine a violin string playing a symphony. Well, these vibrating strings play the tune of all the particles we see in nature. But there's more to it than that. These strings don't just sit there, they move through time, warping the fabric of space along the way. This warp leads to the birth of some wild cosmic creations like black holes and wormholes, totally mind-bending phenomena rooted in Einstein's theories. Superstring theory pulls together Einstein's gravity and the laws of quantum physics into one harmonious framework. This theory is seriously game-changing. It doesn't just bridge two different realms of physics, it opens up a whole new universe of understanding. By viewing particles as vibrations in this universal symphony of strings, superstring theory offers a deep, unified perspective on what reality is all about. In the race for a theory of everything, tons of contenders have thrown their hat into the ring. However, the magic of superstring theory lies in how it weaves together the math and physics of gravity and quantum stuff. This elegant theory isn't just about particles, it's also a window into how space and time work at their core. As these strings move through time, their vibrations shape the very fabric of space, giving rise to cosmic heavyweights like black holes and wormholes, stars of the show in the cosmic drama. The unity achieved by superstring theory is a major leap forward in the world's quest to decode the universe's deepest secrets. Higher dimensions, a 10-dimensional universe. Superstrings are unique because they can only vibrate in 10 dimensions, which plays a crucial role in unifying the fundamental forces of the universe. This idea stems from the notion that 10 dimensions provide ample space to incorporate both Einstein's theory of gravity and subatomic physics seamlessly. To grasp the concept of higher dimensions, imagine a scenario in a Japanese tea garden with carp swimming at the bottom of a pond. These carp, living in a two-dimensional world, are only aware of length and width, oblivious to the concept of height. To them, there's no up or third dimension. If we were to suddenly lift them into our world, they would experience a profound shift into hyperspace, a realm beyond their comprehension. Now, consider when rain disturbs the pond's surface, creating visible ripples. Although the carp cannot perceive the third dimension, they can observe these surface waves. Similarly, we humans cannot directly visualize higher dimensions, but we can detect their effects through vibrations. According to this theory, phenomena like light are manifestations of vibrations traveling along the fifth dimension. Expanding into higher dimensions allows us to accommodate more forces, including nuclear forces, within a unified framework. Simply put, the more dimensions we have, the more forces we can encompass. However, critics of this theory point out that we don't observe these additional dimensions in everyday laboratory settings.